Hello and welcome to Grokking Graph Analytics and Algorithms. Today I want to talk about depth first search, or DFS for short. Depth first search is one of the two basic search algorithms. If you've got any interest in graphs, you're probably already familiar with it. In most cases, it's not the most efficient algorithm, but it does perform really well on some problems and has historical significance. So we're going to briefly cover it and then move on to those more powerful techniques. Depth first search is useful for solving mazes. Here's a simple maze we can use to motivate the algorithm. Let's try solving this maze by hand. We start at the top left and immediately go south. At point 1, we make the decision to go south or east. At point 2, we again make another decision, this time for south or north. At 3, we can choose to either go north or east. At 4, we can choose to go south or north. At 5, we can choose to go east or north again. And at 6, we can choose to go south or north. If we follow the appropriate set of decisions, we can end up at the exit. Let's try to model this maze as a graph. Ask yourself, what are our nodes and our edges? Alternatively, you can ask, what are our entities and our relationships? Go ahead and pause the video and think about what would be appropriate candidates for nodes or edges. Okay, let's try converting this maze into a graph. Pathways such as roads, wires, or in this case, maze hallways are great candidates for edges. Let's mark out our edges and then remove the maze. I've redrawn the maze below. Let's go ahead and mark out our edges. Well, we have our start and our end. And then we have a hallway here and our south hallway. We also have the choice to go east, then south, then north or east, south, north, east, north, south. Let's go ahead and remove the maze walls. Okay, we've removed the walls, and now we have a collection of edges. But in order to have a complete graph, we also need to connect them with nodes. The natural connection between hallways are intersections, so we can treat each intersection as a node. Another question to ask when converting a real-world system into a graph is, where are decisions made? And for this maze problem, decisions are made at intersections. And let's go ahead and connect the start and end as well, treating those as nodes. We haven't put nodes on the ends of hallways. Let's go ahead and do that now. And there you have it. This is our graph represented as a maze. I'm going to change the color of it. There we go. That's a little easier on the eyes. Now that we've got a graph, let's go ahead and revisit our solution strategy. There are two ways to implement depth first search, recursively or with a stack. Let's talk about the recursive solution. To implement a recursive depth first search, you start with a base case, such as the start and end node being the same. Well, if you're at the end node, you've reached the conclusion and you can complete your algorithm. With recursion, we handle a base case, such as having a maze where the start is the end, and then add complexity. So the next more complicated maze is one where we have to make a single decision before reaching the end. And then let's just put a dead end here. This is sort of like saying, I know what to do once I'm at the end. Can I get to the end in one step? Let's try to solve this very simple maze in a recursive manner. We start at the starting node, then we have to make a decision. Do we go towards edge 1 or edge 2? Let's just say we choose to go to edge 1. Well, there's no more decisions to make, but we're also not at the end. Since we have no way to go deeper into our maze, we're going to backtrack. And now we're back at the start, but we've eliminated one of the options. So then we take the next option. This option shows us we're at the end, so we can conclude the algorithm. And that's depth-first search in a nutshell. Let's write out the depth-first search algorithm in pseudocode. The only input we need will be the current node we're on. I'm going to go ahead and call that C. Recall, our final step of the recursion is that we're at the end, in which case we can stop the algorithm. So if our current node equals the end node, then we're finished. Let's go ahead and just clean this up a little. There we go. The next possible option for the node C is that we're at a dead end. And that would look something like this, where C.n is the empty set, where n is the neighbors of C. In that case, we would want to leave this layer of the recursion and go back to the previous one. The last possibility is that C does have neighbors, and that would be handled by iterating through each neighbor. We iterate through each neighbor by calling DFS recursively. That's all there is to the recursive implementation of depth-first search. Let's try to solve our original graph recursively. Well, we start at the starting node, and we can only go towards node 1. Once we're at node 1, we can either choose to go to 7, but that leads to a dead end. So then we backtrack, and now we choose to go to 2. Our next choice is to go to 8, but that also leads to a dead end. So we backtrack, and then the next choice is to go north to 3. We can then choose to go north or east, but if we go north, we end up at a dead end. So we'll backtrack and then go east to 4. And then let's go ahead and make some smart decisions and just go north, east, and then south. The recursive implementation of depth-first search is small and easy to implement. But the only thing it tells us is that we've reached the end. What if instead we wanted a path to solve the maze? Well, for that, we would need an iterative solution.